Hello, here we talk about orders of elements in groups. And also cyclic subgroups are a related concept, related construction. So let's imagine 9 elements in a group. And let's introduce the following notation. So we will think of, it's a kind of a standard notation. Kth power is a product of k copies of G. So if k is a natural number, if it is 0, zero's power, then we'll just choose the identity element for the answer, and if it is negative, so k is still positive natural number, then we just take the inverse and take the product of the inverse k times, k copies of the inverse. So then let's, well, that is just for the future, but I really need this too. So I really need to start looking at the positive, non-negative powers. So if I start looking at those from the 0th power, then the first, then the square, we'll continue forever. We'll have a kth power for any k larger than 2, and then whatever else. But I cannot really continue forever and seeing different answers if my group is finite, if there are only finite number of elements in it. So sooner or later there will be repetition. And how can it be? Well, some power will be equal to something which I computed before. So say equal to the power number k. And that is look good and plausible, but it is not really, because let's look at this equation that some smaller power is equal to some larger power. Well, in the group we have inverses, we have these guys. We can multiply any equation by, or this equation rather, by the inverse of g, and we can continue it k times, doing it k times, and that way we will just get rid of this. We'll get the identity on the left, and then we'll have the smaller power n minus k on the right. We just cancel out j to the k. We can, in groups we have cancellation. So that is a contradiction if we assume that this is the first time when a repetition occurs. It must be happening before, namely at this step, and it must be repeating to the with the identity. So the repetition really goes all the way down to the identity, not to some intermediate step in the group. And here is the concept which formalizes it. So the order of this element in the group is, well, here is notation, is the smallest such power, which is, well, still bigger than 0, which is equal to the identity. It must happen in a finite group, and hence this, at least in finite groups, makes perfect sense. Well, if we have an infinite group, it doesn't have to happen, and in that case there is a second answer, possible answer, it's the infinity. If none of the powers is identity. So that is called having infinite order. Well, again, let me just record the fact that if the group has finite number of elements, if its order is finite, then for any of its elements the order will also be finite. We will have soon we'll have a better characterization, better sort of restriction on those numbers, but right now it's already good enough. So let's now look at cyclic subgroups of elements, or rather cyclic subgroup of a given element G. Well, this is really it. We just look at all possible things we can manufacture out of this element using our group operation. and that will be all possible powers of G, including identity, and also all possible negative powers. So that's what I will just record here. I will just record all possible integer powers as my elements. I'm writing it, as I said, built notation, but I'm not assuming that all these answers are different, because they will be not, say, if the order of G is finite. So if the order of G is equal to n, then really this will consist only of n elements, because at the n-1 step we'll have the repetition. So at the next step, rather, we'll have the repetition. The nth power of G will be the identity. And I'm closing the brackets. I'm not including any inverses because they are automatically there. They are automatically there because of this cycling rule. So n-1 is the inverse of G, because if we multiply both sides by G, we will get the identity. As it should be happening with when we multiply by the inverse. You could see what are the inverses to all other elements in here, so there still be powers in this list, and it's really inverting and sort of taking the minus of the power, but since power n is 0, you are replacing it by n minus the power, so that is the inverse to the power k. And it's supposed to remind you something, modulo arithmetic modulo n, and that is really in an unusual perhaps way an arithmetic modulo n. So let me perhaps finish by an example where, well, this phenomenon of this little behavior, where it can be put to use. So say we are to compute the 99th power of 2 modulo, say prime, which is 101. And we want to find the remainder of this. Well, let's remember Fermat, who says that the hundredth power of 2 is congruent to 1 mod 101. And that is it. So the order of 2, well, we don't know, but we know that the hundredth power is 1. So we can play the same game. We can say that this is as good as 2 inverse. Inverting 2 is usually easier than raising it to this rather big power. So to invert 2, we can really take 101, add 1 to it, because that's what we want to get as a product of 2 and what? Should it be 51? So that says that 51 is the inverse of 2 modulo 101. And so we have our answer. The 99th power is quickly coming down to 51 modulo 101. So that is, of course, you can compute it by taking larger and larger powers and reducing them on the way, but that is quicker, I think. So I'll see you soon with more. Bye.